If you prefer to work in wave numbers like a lot of chemists do, we can actually convert between frequency and wave numbers. We can go ahead and remember that wave numbers are just 1 over wavelengths. That is equal to the frequency over the speed of light. So if we prefer, we can work in these units. We already derived an expression on the last lecture, right? That new absorption is equal to 2 times by b over h times by j plus 1. So now if we want it in terms of wave numbers, all we got to do is divide out by another factor of c. So we got 2b over hc times by j plus 1. Now this gets a little bit silly actually, so this is where I prefer to go ahead and take all of this here and say, well, why are we writing it like that? Let's just call it the rotational constant. So yeah, that's another rotational constant. And at least this one we have the good sense to go ahead and put the little tilde above to remind us that it's in wave numbers. And so we can go ahead and we can write the expression that looks something like this. So it's 2 times by the rotational constant in wave number units times j plus 1. So if we want to look at our spectrum now in wave numbers, we can just go ahead and draw up our wave numbers here on the bottom. And here is 0, and so if j is 0, we get 2 times by b times by 1. So that is a line there at 2b. And when j is 1, we get 2 times by b times by 2. So that's 4b and 6b and 8b and so on. So you see a series of lines that have exactly that same spacing as before of 2b, except now, okay, no Hamlet jokes, okay? So now that we have that spacing in 2 times by b, so 2 of those rotational constants. So we get that comb effect just like we saw before in the frequency space. So here's our pure rotational spectrum from carbon monoxide from that Croto paper. That spacing, I actually went ahead and take a ruler at work. That was back when we were still allowed to go to work, I suppose. And calculated that spacing, and I measured it to be approximately 3.85 wave numbers. And so that means that that spacing is twice that rotational constant in wave numbers. And so that implies that that rotational constant is just half of 3.85. So half of 3.85 wave numbers, right, is 1.925 wave numbers. And what can we do with this? Well, it turns out that this carbon monoxide is actually the isotopomer carbon-12, oxygen-16. And maybe we want to find the bond length of this molecule, so we can actually look up the masses of the two isotopes. Carbon-12 actually is exactly 12 atomic mass units, so that's how we used to actually base the atomic mass unit scale on the mass of carbon-12. And the mass of carbon-16, oxygen-16 is very close to 16. It is 15.995 atomic mass units. And again, an atomic mass unit is 1.6605 times 10 to the minus 27 of a kilogram. So this is very cool. In fact, if we had lab this semester, we would probably do this experiment, but we can take the spectrum here, we can look at the spacing between the lines here in the rotational spectrum, and we can use it to calculate the bond length. So we should go ahead and try and find the bond length, if you can read my writing, from this information. So let's see how we can get the bond length from the spacing in the rotational spectrum, which we know to be 2b. So how are we going to do that? Well, first off, we're working with the b in wave number units. So how do we convert that? And between the b, which we're familiar with in energy units, we know b is h bar squared over 2I, and that has units of energy. So that'll have units of joules, whereas b with a little squiggly on top, the little tilde, has units of reciprocal length, right? So centimeters to the minus 1. So there's an easy way to remember how to do this. So you can take the energy of a photon, E equals hc over lambda. That is the same thing as hc 1 over lambda, which of course is hc times by the wave number. So if we want to convert into wave numbers, okay, we can just take the energy and divide by hc. So that tells us that b in wave numbers is really just b in energy units divided by hc. So that is what we need to play with here. So we know b is h bar squared over 2I divided by hc. So that is h over 2 pi all squared divided by hc and another 2I. So let's go ahead and expand that out. So that is h squared, all divided by 8 pi squared hc, and then I, if you remember, is just mu r squared. So we can go ahead and write mu r squared in there if I can not switch to my eraser tool. So there's mu r squared, and we got some cancellation going on here, right? So we got an h squared on the top and h on the bottom, so we can clean that up. And that gives us a great expression. So let me go ahead and rewrite. So b tilde is equal to h over 8 pi squared c mu r squared. And we're trying to find the bond length, right? So we need to rearrange for r. So let's go ahead and rearrange for r. So this is our expression again on a nice clean sheet here. So we want to rearrange for r. So we can just kind of flip the r squared up to this side, and we can flip the b down to the other side. So that gives us r squared is equal to h over 8 pi squared c mu times by b, which, you know, remember that is half the spacing, right? The spacing in the pure rotational spectrum is 2b. So if we know the spacing, we divide it by 2, right? We get b. And if we want to find r, we can just go ahead and just square root both sides. And so that gives us r, our bond length, is the square root of all this mess here. So h over 8 pi squared c mu times pi, our rotational constant in wave number units. And I think at this point here, we're ready to calculate a couple of things. We need to calculate the effective mass, or the reduced mass. We've already calculated b, so I think we're ready to plug and chug in. So our effective mass, mu, is just the mass of the two atoms multiplied together. So that's the mass of our carbon times by the mass of our oxygen, because we're with carbon monoxide, over the mass of carbon plus the mass of oxygen. And it's easy to look these up in atomic mass units and convert. So you got 12 times by 15.995 divided by 12 plus 15.995 atomic mass units. And well, we'll need things in SI units, so we need to get rid of the atomic mass unit. So we know that one atomic mass unit is 1.6605 times 10 to the minus 27 of a kilogram. And so that gives us a reduced mass, if I did my math right, of 1.138476. That's probably too many significant figures. We're probably good up to here, times 10 to the minus 26 of a kilogram. So I think at this point here, we can just plug everything in. Plugging everything in, so I just rewrote that expression there. So H is 6.626 times 10 to the negative 34th joule seconds. That's the SI unit for energy times the SI unit for time. And we've got an 8, and we got pi. Well, we'll just leave that as pi squared. The speed of light's kind of interesting because we know it is 2.998 times 10 to the 8 meters per second. But we can actually say there's 100 centimeters in a meter, so it's times 10 to the 10 centimeters per second. And that actually helps us here in a bit because our units for B are going to be in reciprocal centimeters. And yeah, we're square rooting this whole shebang. Our reduced mass, right, that was our 1.138476 times 10 to the minus 26 of a kilogram. And if you remember, our spacing was twice as big as B, so our spacing was 3.85 wave numbers. So B is half of that, so that was 1.925, and I could squeeze those units on, centimeters to the minus 1. And we can play the unit game here, and we can see the centimeters and the centimeters to the minus 1 cancel. And well, golly gosh, what are our units going to look like here? Our units right now are going to be the square root of joule seconds over, let's see what we have on the bottom here. We have seconds to the minus 1. So we got seconds to the minus 1. And we also have kilograms. And, oh, I think that's all our units there. If we remember what a joule is a kilogram meter squared per second squared. And we're multiplying that by seconds. And we're dividing that by seconds to the minus 1. Actually, seconds to the minus 1 on the bottom is equivalent to seconds on the top. So we can take that second on the top and square it now. and we got kilograms on the bottom. And I think this is going to look pretty nice here in a second, because we can cancel out the kilograms. We can cancel out the seconds to the -2 with the seconds to the 2. And of course, the square root of meter squared is just meters. And if we're looking for a bond length, meters would be an awfully fine set of units to have. So if we go ahead and we plug this in, we get R is 1.13 times 10 to the -10 of a meter, which we could also write in picometers or nanometers, or if we're going to go rogue, we can remember times 10 to the -10 meter is an angstrom, so 1.13 angstroms. And if we look at our literature value, the literature value for the bond length of carbon monoxide is 1.128 angstroms. So I would say we are pretty close. That makes me very happy.